As always, I'm grateful that you tuned in. This is Professor Jared Rathel. Today, we're going to continue our exploration of community ecology. We're going to be thinking about ecological disturbance events. And by that, I mean things like forest fires, hurricanes, outbreaks of mountain pine bark beetles, how disturbance events impact both the richness and the composition of species found in ecological communities. The Wallow Fire, named for the bare Wallow Wilderness area where the fire originated, was a massive wildfire, the largest in Arizona state history at the time. It started in the White Mountains just outside of Alpine, Arizona. It started on May 29th, 2011. It was started accidentally by two men. They were cousins camping in the Bear Wallow Wilderness. They left for the morning. They thought their morning campfire had gone out, but they were sadly mistaken. So this incredible inferno, shown here from satellite imagery, eventually jumps over the state line into western New Mexico. By the time the fire was contained on July 8th, that means it burned for over a month, it had consumed over 538,000 acres. So my question to you is, how do forest fires like this impact threatened species like the Mexican spotted owl on the top left? Spotted owls are dependent upon old growth forest for their survival. Compare that to the Rocky Mountain elk on the bottom left, which actually does really good in cleared areas because it relies on the grasses and forbs that rebound after the pulse of nutrients provided by a fire. How does the rebound of elk affect the endangered Mexican red wolf? What about species like the 13-lined ground squirrel or the Arizona toad that are not very mobile and are going to have a hard time escaping a fast-moving blaze? Compare that to the Townsend's long-eared bat. Lastly, what about the forest itself? Does it recover? I hope you noticed in that video footage taken 5 years after the Wallow Fire that vegetation was returning to the area. Nature is resilient. Low intensity forest fires are a natural abiotic component within our ponderosa pine coniferous forests here in the high country of Arizona. These forests evolved with fire. What is alarming to conservation biologists like myself is the immense spatial scale and the incredible intensity of recent burns. You may also have noticed from that short clip that in many places the tree mortality was 100%, meaning every single tree died. The fire burned so hot that it jumped into the crown of the canopy and it killed all of the trees. As our climate rapidly warms, Models predict that the western United States, places like the high country in Arizona, will have more frequent and much hotter forest fires. Okay, I have two big ideas that I need you to walk away from this lecture with today. The first is an understanding of the intermediate disturbance hypothesis, or the IDH, often called the Goldilocks hypothesis. Do you remember the Goldilocks fairy tale? It's about a little girl with a penchant for breaking and entering. She recognizes at the bear's house that this bed is too hard, this bed is too soft, but this bed is just right. So it turns out there's a number of parallels to the intermediate disturbance hypothesis in ecology. For an ecosystem to hold the maximum number of species, to have the greatest species richness or biodiversity, you can't have too much disturbance, but you also can't have too little. Number two, I need you to be able to provide me at least one argument, whether you agree or not, supporting this notion that the intermediate disturbance hypothesis is a zombie idea. That is to say, a dead hypothesis that should have been buried long ago, but still clings to existence like a horror movie, like The Walking Dead down here, still clings to existence even in our textbook. An ecological disturbance is a discrete or short-lived event in both time and space that is going to abruptly disrupt, fundamentally change the structure of the ecosystem. It's going to push the community of plants and the associated animals who depend upon those plants back to an earlier successional state. A successional state that's characterized by pioneer species. These are the fast tempo species, like these grasses and forbs that you saw on the video, that have fast life tempos and are evolved to exploit these conditions. The pioneer species are then predictably followed by the intermediate species. These are communities of shrubs and fast-growing trees. The intermediate species are then finally replaced by the climax community. The climax community is characterized by slow tempo species that are good at outcompeting the other species. Okay, so a similar diagram like this is going to show up on your assessment. It may take hundreds of years for a forest, but following an ecological disturbance like a fire or a flood, ecological succession ensues. First, with the pioneer species, then the intermediate species, and finally, a return to the climax community. An ecological disturbance can be caused by abiotic or non-living components in the ecosystem. Things like fire, wind, water, this flooded area on the left, or disturbance can be caused by biotic components, living organisms in the ecosystem. My favorite example, the 43 million red land crabs that live on the small island Christmas Island in the Indian Ocean. So during their annual migration from the forest to the ocean to lay their eggs, these 43 million crabs are going to consume mind-boggling amounts of leaf litter, seeds, shoots, and other vegetation, causing an ecological disturbance. An ecological disturbance can occur from small to large spatial scales. So consider in a tropical rainforest where there's lots of competition for light. When an ancient large tree is blown over by the wind, it creates a small patch of sunlight. And it's going to start this process of ecological succession on the forest floor. Contrast that with the massive palm oil plantations that we talked about in a previous lecture. Some 27 million hectares of rainforest have been cleared on the planet for this incredible disturbance. Just as with spatial scales, an ecological disturbance frequency is going to vary on temporal scales or time scales as well. So, from the great migration of wildebeest in the Serengeti, like the land crabs, this occurs annually, regularly, frequently, to infrequent disturbance events like Mount St. Helens. Volcanoes erupt on millennial timescales. Okay, so for your activity, ecological disturbance and species richness, you'll find it right below this lecture in Canvas. We're heading to the rocky Northern California coast. Okay, not physically, but in our minds, we'll definitely be on the beach, right? So specifically, we'll be exploring one of the most widely cited papers from the journal Ecology. It was published in 1979 by Dr. Wayne Seuss out of UC Berkeley. So Dr. Seuss was interested in the relationship, if any, between the frequency of disturbance events, meaning how frequently does a disturbance event happen temporally, and the resultant species diversity or richness. Would systems frequently disturbed with all those pioneer species, would they harbor a greater biological diversity? Or would it be climax communities that haven't been disturbed in a very long time that house the greatest number of plants and animals? So Sousa's design was brilliant. He reasoned that different sized boulders on the rocky beaches, here we've got a large boulder, a small rock, and a medium boulder, they would be turned over, tossed about, disturbed at different rates depending upon their size. And he measured the force in newtons required to move randomly selected boulders. Some boulders, like these small rocks here, they're frequently disturbed, right? Every time the tide comes in, the little boulders get tossed about. When the tide goes out, they get tossed about again. While other boulders, like the large boulder on the bottom left, they're infrequently disturbed. They might not get disturbed but a few times a century, maybe with a tsunami or a massive thunderstorm coupled with a high tide. So then he measures the number of algal species present, and you can see some here, on these different size classes of boulders. He reasoned that if large boulders have, on average, the greatest number of algal species, then as disturbance frequency decreases, species diversity would rise. Here is what he found. This is Sousa's published table from that original ecology piece. Your task. I want you to use Microsoft Excel or another graphing package that you're comfortable with, and I want you to create a bar graph where the mean number of species is on the y-axis. In order to get the mean, you're going to need to take the average of 1.7, 1.9, 1.9, and 1.4. Get an average. Then you're going to get an average for the intermediate sized boulders, and then you're going to get an average number of algal species for the large, seldomly disturbed boulders. So mean number of species on the Y. On the X, I want you to place the incidence of disturbance, so frequent, intermediate, and seldom. Include a descriptive title, and don't forget to label your X and Y axes with units. Then, in one or two sentences, what do these data support? How does disturbance frequency, either frequently disturbed, intermediately disturbed, or seldomly disturbed, correlate to algal species richness? So about the same time that Sousa's pulling boulders around with spring scales on the Northern California coast, there's another prominent scientist named Joseph Connell who's asking similar questions but at much different scales. So Connell is thinking about how disturbance regimes relate to species diversity, and he looked at the most species-rich terrestrial and aquatic systems on the planet, the tropical rainforests and the coral reefs. Connell argues that these very biologically diverse ecosystems exist in a constant non-equilibrium state of disturbance. Rainforests and coral reefs, Connell argues, have peak species diversity. The number of species in these ecosystem peaks when disturbances are not too large such that they wipe out the whole system, but they're not too small either, which allows for the presence of pioneer species. Connell argues that peak species diversity occurs at intermediate successional states, when there's some pioneers, there's some intermediates, and there's some species from the climax community. And lastly, at intermediate disturbance scales. So you can see the Goldilocks hypothesis. The IDH predicts that species diversity is maximized when disturbance is not too rare nor too frequent, when disturbance is not too large nor too small, when the system is at an intermediate successional state. That's when we're going to get maximum biological diversity. So obviously it's kind of hard to empirically test these ideas, at least at ecosystem size scales. Plus, now's not a really good time to be, massively destroying or disturbing coral reefs. However, we can test these ideas using mathematical simulations. Let me give you an example. So in this simulation, we're going to start with 5 different species, species number 1, 2, through 5. Each population starts with 100 individuals. We're going to vary the amount of disturbance, okay, over 500 time steps. We can consider it 500 years. Caveat: the species on the top here is the best competitor. It has a slow population growth rate, but it outcompetes all the other species. So species number 1 in the Sonoran Desert would be like the saguaro cactus, right? It outcompetes the other species, but it grows very slowly. It takes like 70 years before the saguaro cactus will flower and reproduce. And then we're going to move from slow life tempos down to fast life tempos. So species number 5 has the fastest life tempo. It's not a very good competitor. It gets shaded out by the other species rather quickly, but it does have a high population growth rate. It's very good at quickly reproducing and spreading. So think about the witchgrass seeds that get caught in your socks when you go hiking. This would be a great example for a fast tempo species. Okay, if we simulate these relationships between these 5 different species with a low frequency of disturbance, you can see here we had 3 fires that ripped through the system in 500 years. And those time periods are randomly selected in the model. The simulation has actually been repeated 50 times. You can see that it's been repeated 50 times. And this represents an average of those 50 repetitions. So initially, the blue and gold species, the medium tempo species, they hang on, But then in this long period where there's no disturbance, they die out. So the two best competitors, slow tempo species 1 and 2, those are the ones that are maintained with infrequent disturbance. And you can see here that with 50 repetitions, we average about 2 species that are maintained over 500 years. So this climax community actually has low species diversity. Okay, so now we're going to ramp up the frequency of disturbance. Now we're going to rerun the simulation, and we've got 14 forest fires that are going to rip through during the 500-year period. Who do you think is going to be selected for, and what do you think is going to happen to the number of species in the system? You're right. With high disturbance, in some iterations, species 4 wins, like you see here. In some iterations, species 5 wins out. There's stochasticity or randomness built into these simulations. But the point here is with lots of disturbance, frequent disturbance, most species are being locally extirpated. You can see with 50 runs, we average just 1 species maintained. Finally, let's find out if the porridge is not too hot or not too cold. Let's put in an intermediate level of disturbance. So you can, in this system, you can put in between 0 and 14. We're going to go right in the middle with 7 disturbance events over 500 years. So let's see how this shakes out. Here, species 2, 3, and 4 are maintained, resulting in the highest average species diversity and providing some theoretical support for the intermediate disturbance hypothesis. So, case closed. So, in 10 years, when you look back on this class, what I hope that you remember is that science is a fundamentally different pathway to knowledge. One of the defining attributes of the scientific process is that nothing, no idea is sacred. Prevailing hypotheses they must be tested. So Jeremy Fox, a brilliant ecologist at University of Calgary, created and manages probably the most influential blog in ecology at the moment, Dynamic Ecology. One of Jeremy's most controversial posts from a few years ago now, followed by the opinion piece that you see on the left, is that the time has come in ecology to bury all of those zombie ideas that cling to life in our ecology textbooks, but simply don't have empirical support. The first zombie idea that Jeremy identifies as needing being laid to rest, you guessed it, the intermediate disturbance hypothesis. Jeremy bases his opinion on 2 arguments. I find the first one the most convincing. So there have now been a number of meta-analyses published. A meta-analysis is a research study that looks at lots of different other published research studies or published data sets. So in the age of big data, most of it open source, these meta-analyses, studies of studies, are becoming increasingly popular. But in a meta-analysis, a recent one that looked at over 100 studies, less than 20% of the ecosystems studied actually showed that relationship between peak species diversity or richness and intermediate levels of disturbance. Remember, the validity of a scientific hypothesis rests upon its predictive capacity. A hypothesis that doesn't make accurate predictions is really one that needs to be discarded. It's kind of like the Diamondbacks, the leadoff hitter, right? If the baseball player gets on base 1 out of every 5 times, probably not going to keep his job long. Okay, finally, I have a graded discussion and I really want to know your thoughts. Thus far, we've just talked about how disturbance impacts species richness, meaning the number of species in the system. Count them, how many species are in the ecosystem. But why might a conservation biologist like myself care less about the number of species in the system and care more about the actual composition of species in the system? Which species are actually found there? And I'll give you a hint. I want you to think about the most pervasive form of ecological disturbance on the planet today. You're right. It's us, right? It's us transforming the surface of the planet from the native Sonoran Desert that you see on the right to the green, heavily watered suburban oases on the left. So, how does man made or anthropogenic disturbance like suburban sprawl impact the composition of bird species? In reality, converting Sonoran deserts to suburban oases does not really reduce species richness. You're going to find the same number of species on the left in the neighborhoods as you are on the right in the native desert. However, the species composition, the types of birds that are found in the new suburban habitat compared to the native habitat, the composition is going to change dramatically. The endemic, found no place else, and rare western yellow-billed cuckoo here, the thick-billed parrot, the crested caracara, found here in the southwestern deserts of North America and no place else. They're going to be replaced by pigeons, house sparrows, and European starlings. So, take a moment, post your thoughts. Why might conservation biologists care more about how ecological disturbance impacts species composition more so than species richness? I look forward to hearing your thoughts and I thank you for your time.